Dipole moment. It's a very important property which is present in what? The polar covalent bonded molecular species. See, remember, those molecular species in which the covalent bonds have a polarity, their bonds are called polar covalent bonds, and such molecular species are called polar covalently bonded molecular species. Now, in those molecular species, the molecular species might be having net dipole moment. I told you, always remember, dipole moment is of a bond. Then what happens to the molecule as overall? What will be the overall dipole moment of the molecule? That depends on the basically the geometry of the molecular species. Because all bonds will certainly have certain dipole moments, and since being a vector quantity, we have to now find out the net resultant. See, let us take now the examples. Let us take example of beryllium chloride. This beryllium chloride is having what? Beryllium and chlorine, heteroatomic species. Now, in this, of course, what we find is beryllium and chlorine. These, if we take individual bond, definitely chlorine will be having a partial negative charge, beryllium will be having a positive charge, and the same is this. But since the structure, the geometry of the molecule is linear, the dipole moment of this bond and dipole moment of this bond are exactly opposite in directions. Their magnitude is same, but they are opposite in directions. So the net dipole moment will be 0. Remember, if this is the dipole moment for this bond and this is the dipole moment of this bond, the resultant dipole moment is always given as, it's a vector, we have to find out the resultant. So it will be nu1 square plus nu2 square plus 2 nu1 nu2 cos theta. So since here the angle was 180 degree, this becomes what? 0. Gets cancelled and becomes 0. So this is most important, that with the help of this formula we have to find out the resultant dipole moment of the molecular species, which depends on the dipole moment of its individual bonds. And that is basically depending upon the basic geometry of the molecular species. Let us take some other examples, like we have boron trifluoride. Boron trifluoride is having trigonal planar structure. In this trigonal planar structure, each fluorine is, of course, is more electronegative than boron, so will have a partial negative charge. Boron will have a partial positive charge. Dipole moment of this bond is towards this side, of this fluorine is towards this side, and of this fluorine is towards this side. Since the angle is 120 degree, the resultant of these two dipole moments will be on this side. But since these two will be opposite to each other, this one will be opposite to this, they get cancelled. So the net dipole moment even in this case is what? Is 0. So this is what we find out the net dipole moment of the different molecular species. Now let us take very two important examples to discuss this. We can take the example of ammonia and NF3, nitrogen trifluoride. Now both these molecular species are having same structures, almost same structures. The geometry is same, it's pyramidal. What we find is, in case of ammonia, they have 3 hydrogen atoms like this, and there is a lone pair above it. In case of nitrogen trifluoride, again the structures are same, geometry is same, but in place of hydrogens we have 3 fluorine. Now out of nitrogen and hydrogen, we know nitrogen is more electronegative and hydrogens will acquire a partial positive charge. So the dipole moment of all these bonds are towards nitrogen, and what we find is that the experimental dipole moment is found to be more than the net dipole moment. In this case, why the experimental is more than the net? The reason is, we forgot to add the dipole moment due to lone pair. This lone pair also is having dipole moment. This is negatively charged electrons separated by a distance from the positive nucleus of the nitrogen. So lone pair also has a dipole moment, and since the dipole moment of lone pair is along the side of the net resultant dipole moment, they both gets added up. That's why the experimental value is more than the net resultant. Whereas in case of NF3, since fluorines are more electronegative than nitrogen, what we find is all dipole moments of the fluorine nitrogen bonds are away from nitrogen. So definitely the resultant one is downward side. Whereas the lone pair's dipole moment is opposite to this one. So what we find in this case is the experimental value is less than the resultant one. Why? Because this dipole moment of the lone pair is subtracted from the resultant one. That's why this is less than the resultant one. So this is how we try to find out the resultant dipole moments. Of course, these dipole moments plays an important role, because if the overall molecular species is having a dipole moment, definitely it will develop dipole-dipole interaction with the other type of molecular species. So this is how their boiling points will be high, their melting points will be high, they can be more miscible with each other and with the other polar molecular species. So these are the certain things, basic things, which depending upon their individual bonds decides the physical and the chemical properties of these molecular species.